Okay, thank you very much, Howard, for the introduction, and it's a great personal pleasure for me to be here speaking in Brazil for the first time. So I'd like to talk mainly about work from around 2014 and 2015 on gap stream primes, but those of you who had the pleasure to go to the previous ICM will maybe remember that there were several talks at that ICM about gap stream primes, and so this can be seen as a natural extension of some of the results that were talked about then. It's a very exciting time for work on prime number theory. But for those of you who weren't at the ICM beforehand, don't worry, this is aimed at a general mathematical audience and will be completely self-contained. So maybe the most basic question in prime number theory is to try and understand the distribution of prime numbers. So maybe the most basic question in prime number theory is to try and understand the distribution of prime numbers. And in my mind, there's two sets of questions. There's large-scale questions about gap stream prime numbers, which often lead very quickly to questions related to the Riemann hypothesis. And then there's small-scale questions related to prime numbers, which look at correlations of the primes and questions about the gap stream primes. So I'd like to talk about gap stream primes today and try and understand something about the distribution of the gap stream primes. So maybe the most basic and celebrated result in prime number theory is the prime number theorem. And this says that if you want to count the number of primes up to some large number x, then the number of these primes is roughly x divided by the logarithm of x. So another way of viewing this is if we look at primes of size roughly some large number x, then the average gap between prime numbers is of size the logarithm of x. So since the logarithm of x gets larger, as x gets larger, the primes get sparser and sparser, and on average, the gap between primes gets bigger and bigger and bigger. When you're looking at primes of size x, you get a gap typically of size the logarithm of x. But the question I want to think about today is whether it's the case that you always get gaps that look roughly of size the logarithm of x, or if in fact it's the case that you get sometimes gaps which are rather smaller than log of x, and sometimes gaps which are rather larger than log of x. So the extremes of the gaps between primes. How small a gap can you get, and how large a gap can you get? So this is the basic question that I like to think about today, and I'm going to start off by thinking about the question of small gaps between primes. So how small can gaps between primes be? Maybe ideally you'd have some complete classification of all small gaps between prime numbers. So let's try and start off by doing this. The smallest possible gap between primes is size 1, and it's quite easy to see that the only pair of primes that differ by exactly 1 are the primes 2 and 3, for the simple reason that any two consecutive integers, one of them has to be a multiple of 2. So we've got a complete classification of all prime gaps of size 1. Now let's try and get a complete classification of all prime gaps of size 2. So we can start doing some calculations. We find 3 and 5, 5 and 7, 11 and 13, but there seems to be lots and lots of these pairs of primes. The first pair bigger than 1,000 is 1,031, 1,033. First pair bigger than 1,000,000 is 1,037, 1,039. The first pair bigger than 1 billion is 1,007, 1,009, and these seem to keep on coming. So maybe the natural guess, just from this quick computation, is that there should be infinitely many such pairs of primes which differ by exactly 2. And as I'm sure virtually everyone in the audience knows, this is the famous twin prime conjecture, which is one of the oldest and most famous problems in mathematics, but unfortunately it's very much open and we really don't know how to solve this, even if it's perhaps one of the most basic questions you could possibly ask about prime numbers. But even though the prime number theorem, the twin prime conjecture is very much open, it turns out for lots of the recent progress on small gaps between primes, it helps us to try and look beyond the twin prime conjecture and at least guess at what might be true beyond that. So maybe you'll humor me and let me think about more general gaps between primes. So we can look at gaps between primes not just of size 1 or 2, but of size h for any given integer h. And we get a very similar phenomenon that if we're looking at an odd number h, then one of the two integers that we're looking at must be a multiple of 2, and there's only one prime which is a multiple of 2, and so clearly there can't be infinitely many primes that differ by any given fixed odd number. However, when we're looking at prime gaps of size 4, or prime gaps of size 6, or prime gaps of size 8, for each of these, we find lots and lots of pairs of primes that differ by exactly that number. And therefore, again, as a generalization of the twin prime conjecture, known as the Polignac conjecture, still well over 100 years old, is that not only should there be infinitely many pairs of primes that differ by exactly 2, but in fact there should be infinitely many pairs of primes that differ by exactly h for any given positive even number h. But we don't even need to stop there. Rather than just looking at pairs of primes, we could think about clusters of many primes. We could consider 3 primes or 4 primes all clustered very close together. So we could think about how short an interval can you fit 3 primes in. And if you're looking for triples of primes all contained in an interval of length 5, then there's only 4 possibilities: 2, 3, 5, 2, 3, 7, 2, 5, 7, or 3, 5, 7, for the simple reason that in any interval of length 5, you have to have one integer that's a multiple of 2, or you have to have one integer that's a multiple of 3. And there's only one prime which is a multiple of 2, and there's only one prime which is a multiple of 3. However, if you're looking instead for primes in intervals of length 6, then we find there's lots and lots and lots of triples of primes all contained in an interval of length 6. And so naturally you would guess that there's infinitely many. And I just want to take this sequence of generalizations one step further, where instead we consider k different linear functions. So these are just linear functions an plus b as a function of n for 2 given integers a and b. So you choose your favorite k of these, let's call them L1 of n, L2 of n, up to Lk of n, and the question is it the case that there's infinitely many integers n, such that all of these functions are simultaneously prime, or is it the case that there's only finitely many integers n when these linear functions are simultaneously prime? And so this is known as the prime k-tuples conjecture, and in exactly the same way that we saw before, that there can be some obvious obstructions to linear functions being simultaneously prime, because one of the functions has to be a multiple of 2, or one of the functions has to be a multiple of 3. There's an actual generalization of this, which classifies any silly reason why they can't all be simultaneously prime, which is that one of them always has to be the multiple of some fixed prime p. However, if there's no such obvious congruence obstruction, then the conjecture is known as the prime k-tuples conjecture, that there should be infinitely many integers n, such that all the linear functions are simultaneously prime infinitely often. So another way of saying this is, you give me your linear functions, there's a very quick and easy check to see whether there should be some obstruction to them being simultaneously prime. If there's not one of these simple obstructions, then we believe it should be the case that they're simultaneously prime infinitely often. And the prime k-tuples conjecture is really a very powerful conjecture that tells us almost everything we want to know, at least from a qualitative sense, about the small-scale distribution of prime numbers. So it immediately implies the twin prime conjecture, but it implies a lot more besides that. So not only do you get 2 primes very close together, you get m primes very close together, and in fact you can have m primes all contained in an interval of length roughly m log m, so really very compactly, tightly together. It implies straight away that you have infinitely many Sophie germain primes. 2 immediate consequences of this are infinitely many cases of Fermat's last theorem, and the open problem of Artin's conjecture on primitive roots would follow from the infinitude of Sophie germain primes. Maybe everything I've mentioned so far sounds very much about pure number theory and analytic number theory, but the twin prime conjecture also has the existence of various prime configurations that are very relevant for the function of computer algorithms. So there's the concept of safe primes, for example, and it implies that there are infinitely many safe primes, which is a certain type of prime number that's found for certain computational cryptographic algorithms. A few more immediate consequences that you get arbitrarily long arithmetic progressions of the primes, so another proof of the Green-Tau theorem, but moreover you can have this with bounded gap stream primes at the same time that you're finding. You also find that Goldbach's conjecture is a fairly immediate consequence of a slight generalization of the prime k-tuples conjecture, where you have to be slightly careful about uniformity. And you can also find a residue class mod Q that contains many small primes, which is a problem that will crop up towards the end of my talk. So hopefully I've convinced you that the prime k-tuples conjecture is a really big conjecture that has fantastic consequences for the prime numbers, but being a huge generalization of the twin prime conjecture, unfortunately it's well beyond anything that we're able to prove at the moment. However, the main result that I'd like to talk about is a weak form of the prime k-tuples conjecture. So if we recall the prime k-tuples conjecture, you choose your favorite k-linear functions. There's a simple check as to whether there's an obvious congruence obstruction, but if they're admissible, then we believe it should be the case that they're infinitely many prime. They're simultaneously prime infinitely often. And the theorem that I'd like to talk about says that rather than demanding that all of the linear functions are simultaneously prime, we can guarantee unconditionally that at least many of them are simultaneously prime. So instead of having all k of L1 of n and Lk of n being simultaneously prime, in fact I can have roughly log k of the linear functions being simultaneously prime. So a few quick comments I'd like to make about this. Famously, Zhang proved his result about bounded gap stream primes, and that roughly corresponds to a version of this weak prime k-tuples conjecture, where instead of having log k of the linear functions being prime, he had 2 of the linear functions being prime, provided k was large enough. And he proved this using a different method. However, even though his method was different, both the ideas behind this proof and the ideas behind Zhang's proof are rooted in earlier work of Goldson, Pintz, and Yildirim. So this result was due to me, but also independently Terry Tao around 2013, 2014. And from a technical point of view, it's also very useful because the method is very flexible and can apply to lots of other situations. So we can prove weak forms of this prime k-tuples conjecture in lots of different contexts now. So I'd like to begin by giving a few ideas about how one might go about proving such a weak form of the prime k-tuples conjecture. Oh, sorry. But before that, I'd like to mention the immediate consequences for gap stream primes. So if we recall, Zhang's theorem said that you had 2 of your linear functions being simultaneously prime, provided k is large enough. If you choose all your linear functions just to be of the form n plus bi for some constants bi, chosen such that they're admissible, then you automatically find that when 2 of them are simultaneously prime infinitely often, you get infinite many pairs of primes that differ by some bounded amount, because the linear functions themselves are fixed. And when you go through Zhang's argument numerically, he got that there were infinitely many pairs of primes that differed by at most 70 million. The weak form of the prime k-tuples conjecture that I put up before not only gives bounded gap stream primes, but it turns out that the method gives an improved numerical result for bounded gap stream primes. So I was able to show that there are infinitely many pairs of primes that differ by at most 600. And moreover, because I could get many of the linear functions being simultaneously prime, I was able to show that there are bounded length intervals that contain many primes infinitely often, not just bounded length intervals containing 2 primes. Then in subsequent work as part of the Polymath collaborative online project, we optimized the numerics involved in the argument, and the current world record is that there are infinitely many pairs of primes that differ by no more than 246. So I'd now like to move on to a couple of the ideas in the proof. And on a very high level, I like to think of the proof as an application of the probabilistic method. So you take some large number x, and I want to choose an integer n between x and 2x at random according to some probability measure. And I want this probability measure to be biased so that it's highly concentrated on when many of the linear functions that we fixed are simultaneously prime. And then I now want to just perform one computation. Given this random integer n that I've chosen, I want to calculate the expected number of the linear functions which are simultaneously prime. And if I find this expectation is large, say, imagine I do the computation and I find that the expectation is 10.5, that means that for at least one integer n between x and 2x, there must be 11 of the linear functions being simultaneously prime. And so, provided I can compute this expectation, and this expectation is large enough, I can show that many of the linear functions must be simultaneously prime for at least one value of n between x and 2x. And if I can repeat this argument for all large values of x, then I must have found infinitely many integers n such that many of the linear functions are simultaneously prime. So that's a very high-level overview of how the argument works. It's worth noting that I don't know which of the linear functions are simultaneously prime at all. I'm just guaranteeing that some of them are simultaneously prime, and I don't know which integer n this occurs for. I'm just guaranteeing the existence of some integer n. So if you accept this strategy, then the question then becomes, how on earth do I choose this probability measure? There's two requirements which are competing in different directions. On the one hand, the probability measure has to be simple enough so I can perform the computation where I can calculate this expectation. But on the other hand, it has to be complicated enough so that it's really capturing something to do with the prime numbers. If I just chose a simple smooth function, for example, for the probability measure, then because the primes have zero density, this expectation would be decreasing as a function of x, and it would be less than 1 for all large values of x, and the method wouldn't prove anything at all. If, however, I chose a function that's very tied up to the twin prime conjecture, then it's unlikely that I could calculate the expectation. But fortunately, there's an area of analytic number theory known as Sif methods, which are very well suited for precisely these sorts of questions. So to give a very high-level overview, I view Sif methods as the study of certain weighted integers which you can think of almost primes or approximate prime numbers. The idea is that you give every integer n a non-negative weight according to some approximate degree of how prime it is. And the hope is that these non-negative weights are much easier to calculate with than the prime numbers themselves, but nonetheless capture much of the arithmetic interest that we have with the prime numbers. And so there's two key properties about these Sif weights that come up, that provided you understand the underlying integer solutions in arithmetic progressions, you can compute things using these Sif weights. And for our question about simultaneous prime values of linear functions, because we understand the primes themselves fairly well in arithmetic progressions, and we understand the integers in arithmetic progressions, we can compute using these Sif weights. The other key property is that the primes have positive density when you consider integers weighted by these non-negative weights. So although the primes have density 0 in the integers, they have a positive density inside these weighted integers. They have a positive weight, a positive proportion of the whole weight. And so this means that the almost primes are genuinely capturing some of the arithmetic complexity of the primes, and so can be thought of as a natural way of interpolating between the integers, which we understand well, but are arithmetically too naive, and the primes, which are what we want to understand, but are very difficult to compute with. So, given that we understand the problem of linear functions well in arithmetic progressions, and we know that the primes have positive density in the almost primes, we expect that we can perform a computation if we choose a probability measure defined naturally in terms of these Sif weights. And moreover, this final expectation should tend to some positive value. However, there's still the question as to what that positive value is, because if I find the expected number of my linear functions which is simultaneously prime is 1/10, then this doesn't prove anything at all. It just proves that there's infinitely many primes. It doesn't show that there's simultaneous prime values. So I only get a result about bounded gaps between primes, provided I can show that this expectation is bigger than 1. And all I know from this slide is that the expectation should be positive, but it could be a very small positive number. And therefore, what the precise value of the expectation is depends very much on the precise definition of almost prime. And it turns out that there's still a little bit more of an art than a science in terms of precisely how you define these Sif weights for different applications and precisely what sort of expectations you get out. So the question of choosing a probability measure, if we decide to define it in terms of these Sif weights, then boils down to a precise choice of the sieve that we would want to use. And it turns out that there's a fairly standard choice, and it's the Silberg sieve that performs exceptionally well in these sorts of circumstances and is often optimal. And if you take this off-the-shelf result, you can perform the computation, and you find that the expectation that you get is roughly a half when x is very large. So this is somewhat disappointing. We've completely failed to prove bounded gaps using what is often the optimal choice of sieve weights. However, it was a remarkable result of Goldston, Pinson, Theorem, and this was the key part of their method, that you can perform a modified version of the Silberg sieve that actually performs much better. And so they produced a different type of sieve, and when you perform the computation, this gives a number which can be made arbitrarily close to 1, but is always slightly smaller than 1. So this is really frustrating, because it means we just failed to prove bounded gaps between primes using their ideas. However, as I mentioned, the underlying arithmetic input for performing these computations relies on results about integers and primes in arithmetic progressions, and the key breakthrough of Yuteng Zhang was to prove a slightly stronger result about primes in arithmetic progressions. And so because he produced slightly stronger basic arithmetic information, he could correspondingly put this into Goldston, Pinson, Theorem's argument, and this just improved the expectation a very small amount. But because we were just below the threshold beforehand, this was enough to push us just over the threshold, and this was how Zhang proved bounded gaps between primes. However, the key idea in my work was a multidimensional generalization of the Silberg sieve, which performed much better at transferring this arithmetic information about results in arithmetic progressions to results about small gaps between primes. And so by coming up with a new type of sieve, I was able to show that the expected number of the linear functions which are prime was roughly log k divided by 4. And so not only do you get 2 of the functions being simultaneously prime, because we can get an expectation slightly larger than 1, when k is large enough, you can have 10 or 100 or 1,000 of your linear functions being simultaneously prime. So just to give a schematic overview to the idea of the method, we'd like to prove an arithmetic result about small gaps between primes, and the key arithmetic input that fundamentally the whole method relies on is results about primes in arithmetic progressions. And to turn the sort of arithmetic information that we know about primes into the sort of arithmetic information that we'd like to know about primes, we use this sieve method and the random probabilistic argument based on the sieve. And this transfers results about primes in arithmetic progressions in principle to results about small gaps between primes. Zhang's key result was to improve the arithmetic information feeding into the whole method, which correspondingly flowed through the whole diagram and produced stronger results about small gaps between primes. And fortunately, because we were right on the cusp of proving bounded gaps between primes, thanks to the work of Goldston, Pinson, Theorem, this was enough to give us bounded gaps between primes. Rather than working on primes in arithmetic progressions, my work was about the sieve method at the heart of this argument, about transferring the information about primes in arithmetic progressions to small gaps between primes, and my multidimensional generalization was more efficient, and so using even just weaker results about primes in arithmetic progressions, it was able to prove much stronger results about small gaps between primes and gaps between many primes. This doesn't completely tell the full story, because to get good results about small gap stream primes, you need to optimize many auxiliary choices of parameters in the Sif method. And so you need to solve a few different separate problems, one just pure combinatorial problem, and one pure analysis problem, which is an optimization problem based on the choice of smooth weights. It turns out that these can be solved using ideas from elementary number theory and combinatorics, or ideas from either numerical analysis or functional analysis with a bit of probability theory thrown in to get good results about small gap stream primes and to optimize all the parts of the method. If, for example, you care very much about the numerical results, for example, the polymath result, which is the current world record, that there's infinite many pairs of primes that differ by no more than 246. This 246 is an unnatural number that's just an artifact of the method. The method with the new sieve makes it clear that you will get some numerical bound. The precise value you get is dependent very much on how well you can solve this optimization problem and how well you can solve the combinatorial problem, both of which we have essentially optimal answers for now. But there's a natural loss in the argument based on this moving to approximate prime numbers. And this means that we don't get twin primes using this method. We can only get 50 of our linear functions. If you choose 50 linear functions, you can ensure that 2 of them are simultaneously prime. And these 50 linear functions, once you choose them to be as tightly packed as possible, being admissible, corresponds to the result that there's infinitely many pairs of primes that differ by no more than 246. So 246 is just an artifact of the method, but also if you could prove strong results about primes in arithmetic regressions, then correspondingly this would feed through and get strong results about small gap stream primes, and would be one way to improve the 246. I'd now like to pass to the opposite extreme. So I've talked a bit about prime k-tuples conjecture and its consequences for very small gap stream primes, and in particular gap stream primes that are much smaller than the average gap of size the logarithm of x. I'd now like to think about large gap stream primes. So again, if we look at primes of size about x, then the prime number theorem says that the average gap is of size log of x, so we certainly have gaps which are of size at least log of x in their order of magnitude. And the question I want to consider is, how much larger can they be than the logarithm of x? Or maybe it's the case that even the largest prime gaps are only a little bit larger than the logarithm of x. Well, it turns out that it was the result in the late 1920s of Vesinthius that there exist prime gaps which can be arbitrarily large compared to the average gap. And there was then a flurry of papers through the 1930s which were optimizing these results, and they stabilized in Ranking's 1938 result that you can get gaps which are quantitatively bigger than the average gap. So rather than having gaps of size log x, you can have gaps which are slightly larger than the size log x, which are given by this rather messy expression, log x times double log x divided by triple log x squared times quadruple log x. But really you should think of this as something which is slightly smaller than the log of x times the double log of x. And unfortunately, progress then stopped after this flurry of papers in the 1930s, and beyond very minor improvements to an implied constant, there were no real improvements on Ranking's results. So for those of you who remember Paul Erdos or have heard about Paul Erdos, he used to encourage and stimulate work in the combinatorics and number theory communities by offering challenge problems to different researchers, and as an incentive, he would put monetary rewards on solving the different problems that he set to the community. And it turned out that Erdos, who had worked on this problem and was amongst the authors behind in the sequence of papers leading up to Ranking's result, he was very taken by this problem, but acknowledged that to make any progress, significant progress beyond Ranking's result, you needed fundamentally new arithmetic input and new arithmetic ideas. So he actually put the largest reward that he ever put on a problem for this particular problem, and he challenged the community merely to improve this result by the smallest possible amount. So provided you could show that there was a function which grew faster than a constant times log x times double log x divided by triple log x squared times quadruple log x, he put a $10,000 reward, and he did this because it clearly required new arithmetic ideas. So in 2014, this was independently solved by myself and a team of 4 authors of Kevin Ford, Ben Green, Sergei Kunyagin, and Terry Tao. Since then, the 5 of us have combined our efforts to get the best possible quantitative result from our new approaches, and we get a small but modest improvement over Rankin's results. So we improve this triple log x squared on the denominator to a triple log x. So maybe the quantitative improvement is not so exciting in and of itself, but the key point is that we're able to input new arithmetic information into the whole method. So I'd now like to go through a couple of slides of some of the ideas behind the proof of producing large gap stream primes. And I like to think of the fundamental problem of producing large gap stream primes as a game. So I give you some large integer y, and then we line up the integers 1 up to y. And the way the game is played is that first of all you choose a residue class mod 2, and we cross out all integers which are congruent to your residue class mod 2. So if you choose a2 mod 2, then we cross out all integers which are congruent to a2 mod 2. Then we go to the next prime, which is 3, and we cross out all integers which are congruent to a3 mod 3. And then we keep on doing this prime by prime. You choose the residue class a5 mod 5, then a7 mod 7, and then each time we cross out all the integers in that residue class. And we keep on going until you've crossed out all the integers between 1 up to y. And the fundamental problem is what's the minimal number of steps? If you choose your residue classes very cleverly, how quickly can you get to the end game where we cross out all integers between 1 up to y? If you can cross out all the integers very quickly, then there's a trick based on the prime number theorem that shows that you can create a string of consecutive integers, each of which has a very small prime factor, and so you've created a long string of consecutive integers, and therefore a long string of numbers which aren't prime, and therefore a large gap between primes. So this is a very natural generalization of maybe the high school argument that you can remember that there should be arbitrarily large gaps between primes, because n factorial plus 2 is a multiple of 2, n factorial plus 3 is a multiple of 3, n factorial plus 4 is a multiple of 4, and so on up to n factorial plus n is a multiple of n. And so this is giving you n minus 1 consecutive composite values, and so it's giving you a gap between primes of size at least n. And this is just a very natural generalization of that, which can be formulated and thought of as this combinatorial arithmetic game. So the aim then is to try and come up with a choice of residue classes which very efficiently cross out all numbers 1 up to y, and so you want to try and as much as possible avoid repeatedly crossing out the same number using a bad choice of residue classes. And the argument based on Erdős ranking is very simple. For medium-sized primes, you just choose the residue class 0. And then for small primes and large primes, you just greedily make a choice of the residue class which will cross out the most number of points at that stage. And by analyzing this algorithm for how you play the game, they showed that you require about y times the double log of y divided by log of y primes. And this correspondingly, once you've optimized what you mean by medium, small, and large, and once you plug this result back into what I had on the first slide, this gives Rankin's result on large gap stream primes. So it's this argument that we'd like to improve upon by being more careful with our choices of the residue classes by inputting some extra arithmetic information about the primes. And the argument behind my work with Ford, Knyag, Green, and Tao is improving the choices of the residue class for large primes. Now, I don't want to go through all the details, but it turns out that the fundamental obstacle is a fairly simple question about prime numbers. We'd like to choose some residue class. It turns out that for the Erdős-Rankin method, the residue classes chosen for the large primes, you only need to guarantee removing one prime at each stage, whereas we'd like to remove many of the remaining survivors that haven't been crossed out yet. And once you work through the argument, this is morally the same as the problem of I give you some prime of size about x, and you need to find some residue class, AP modulo P, which contains many primes which are only very slightly larger than x. So AP mod P contains just one residue class modulo something of size about x, so there's only about one element amongst primes which are of size x, but if we go slightly larger than x, then we might hope that we can find many primes which are all in the same residue class, although because the primes have density about 1 over log x, on average, there are no primes in any of these residue classes. So we want to find some rare residue class which is unusually rich in the number of primes. But this is precisely the sort of problem that I mentioned was a consequence of the prime k-tuples conjecture, at least if you knew the prime k-tuples conjecture with good degrees of uniformity in lots of the parameters. So you could choose your linear functions to be of the form Li of n goes to n plus some small multiple of p, where you choose these small multiples to make the linear functions an admissible set of linear functions to avoid the obvious concurrence restrictions. And provided you can find an integer n, which is not much larger than p, satisfying this, you'd then find a residue class, an integer n where many of these linear functions are simultaneously prime, corresponds to a residue class containing many small primes. So we don't know the prime k-tuples conjecture, but we do know our weak form of the prime k-tuples conjecture, and I mentioned that one pleasing feature of the method is that it's very uniform and flexible, and so in particular, using our weak form of the prime k-tuples conjecture with this sort of choice of the linear functions, we can solve this model problem and show that for any prime p of size about x, there has to be a residue class AP mod p, which contains many primes which are only a little bit larger than x. Now, having solved that middle problem, we then use techniques from probabilistic combinatorics to show that one can make a consistent choice of the residue classes AP for all the large primes P to more efficiently go through the Erdős-Rankin argument, and so to play this combinatorial game where we're crossing out integers more efficiently, and this requires rather fewer primes in the overall argument, and correspondingly gives us rather larger gaps between primes. So I just want to finish with a few concluding remarks. So one question that I left open was the fact that the whole method of proving these weak forms of the prime k-tuples conjecture relied on our results about primes and arithmetic progressions. And so if one was very optimistic, we might say, well, what if we assumed as optimistically as possible the strongest believed results about primes and arithmetic progressions? How far can we possibly push this method? And so it's a result as part of the work in the polymath group that if we assume the most optimistic results about primes and arithmetic progressions, which is a conjecture known as the generalized Elliott-Halberstam conjecture, then we can push this method much further. We have much stronger arithmetic information feeding into the sieve, and so we can get much stronger results about, for example, small gaps between primes. And in particular, we can show that there's infinitely many pairs of primes that differ by no more than 6. However, unfortunately, this is a hard limit for our methods, and there's a very substantial obstruction for trying to push 6 down to 2 and prove the twin prime conjecture. So it's definitely the case that a new fundamental arithmetic idea is needed, even if we were to assume exceptionally strong results about primes and arithmetic progressions, if one wants to prove the twin prime conjecture itself. It's a fundamental part of the method that we don't know which functions are simultaneously prime, and therefore we can't prove the twin prime conjecture. However, this does have a couple of amusing consequences, one of which I'd like to mention here. So if you assume this very plausible and widely believed, but definitely very optimistic result about primes in arithmetic progressions, then at least one of the following results is true. Either the twin prime conjecture is true, or it's the case that the Goldbach conjecture is almost true, in the sense that every large even number is within at most 2 of a number which can be written as the sum of 2 primes. Now, of course, we believe that both of these two things should hold, and I can't tell you either one of them holds, but I can't tell you individually either one of them holds, but I know that at least one of the two holds as a consequence of these results. So, just to finally wrap up, there's been a lot of very exciting developments on gaps between primes and prime number theory. It's a great time to be involved in analytic number theory and Sif methods. For young people, it's a very energetic field at the moment. It's a very exciting time. I think there's been a number of great results. Maxime Radziwiłł will be talking later on in this congress about other results related to the twin prime conjecture from a slightly different angle. I hope you enjoyed the talk. Thank you very much for listening. I think I'll wrap up here and pass over to questions. Thank you very much.
Thank you very much, James. Can we have a few questions? Questions?
Can you just explain a little bit more about the optimization problem in the small gaps proof?
Sure. So there's two different optimization problems. One of them, I said that you take your linear functions to be of the form n plus bi, so just some linear shifts, but you want to choose the bi's which can be as close together in size as possible, so as smaller numbers as possible, while still maintaining the fact that you don't have one of these obvious congruence restrictions to all the linear functions being simultaneously prime, to get the best possible result about small gaps between primes. So this is the combinatorial optimization problem of how small can I choose these linear shifts bi to keep my set being admissible, but have them as closely supported as possible. And it turns out that we have numerical computations for small values of k, and we have asymptotically optimal results for large values of k for that optimization problem. The second optimization problem is slightly more subtle. So I mentioned that the key idea in my work is a multi-dimensional generalization of the Selberg sieve. And naively, this is defined in terms of some auxiliary parameter, which is fundamentally corresponding to a multi-dimensional version of this probability distribution function. And this is, and there's a question as to how do I choose this smooth function optimally in terms of to try and get the best possible result and make the sieve as efficient as possible. And this correspondingly turns out to be to calculating the largest eigenvalue of a certain linear operator on Hilbert space. So you can define a fairly nasty looking linear operator which is corresponding to this expectation, which is a function very closely related to calculating this expectation for the number of simultaneous prime values. And to get the optimal result, you want to calculate the largest eigenvalue of this linear operator. To get a result, you need to bound the spectrum of the linear operator. So this is a pure functional analysis problem that has stripped out all the number theory, but this is precisely the problem that you want to solve. And morally, what's going on when you're choosing this optimal function is you're trading off between trying to increase the probability that all your linear functions are simultaneously prime versus decreasing the probability that they're simultaneously prime, but increasing the probability that at least one of them is prime. And there's a trade-off there, and that's captured by this linear operator. But the precise details may be too technical for me to say now.
Yeah, I have a question which has nothing to do with analysis. So in your Erdős-Rankin method, where you had to go to the sieve, and then you wanted efficient sieving techniques, has anybody tried to refine that using properties of primordial numbers? So instead of dealing with factorials, but products of primes, to sort of make the sieving process go easier?
Right, so yeah, we're using the high school method is maybe n factorial plus 2, n factorial plus 3, really choosing if you chose the residue class 1 for every prime, that would be corresponding to taking n primorial plus 2, n primorial plus 3, n primorial plus 4. So yes, that's already incorporated in this, and that would be corresponding to the most basic choice of just choosing one residue class always equal to 1 at every stage. But it turns out that there's these more complicated choices of residue classes which work more efficiently. But yes, that's very much incorporated.
Very well.
So what is the expected order of GX for large prime gap?
So that's a very good question. So it's strongly believed that if you're looking at primes of size about x, the largest gap between primes should be of size about log x squared. So this is rather larger than any of the results we have so far. Our methods are somewhat limited, and in fact, all our methods go through this combinatorial game, and it's strongly believed that if you go through this combinatorial game, you can't get close to proving log x squared. So somehow large gaps that occur in nature occur for very different reasons to the ones that we're constructing here, but we need a radically new idea to be able to touch that. But amongst primes of size about x, we expect the largest gap to be of size log x squared.
Other questions, please? May I ask another foolish question? Yes, so you have, all right, so Bloomire-Vinogradov is a result with level of distribution 1/2, meaning it tells you that the primes are equidistributed on average for moduli up to size about x to the 1/2. Now, if you assume you have already told us what happens when you assume Elliott-Halberstam, that is level of distribution 1 minus epsilon, roughly. What about all the levels of distribution in between? I assume that gradually helps. And what happens if you assume a level of distribution of 1/2 plus epsilon? Does that make a difference?
So I mentioned that you get about log k over 4 of your linear functions being simultaneously prime. If you assume that instead of having level of distribution 1/2, you have level of distribution theta, then you get
all right.
theta over 2 times log k of your linear functions being simultaneously prime. So it affects that. That's the numerical consequence. And then that correspondingly, as you get a slightly better level of distribution, you can get slightly more of your linear functions being prime, or you require slightly fewer of your linear functions to ensure that 2 of them are simultaneously prime.
So it's as close to continuous as a function from the reals to the integers can be.
Yes, exactly.
Yes. And what about results in the mold of Jean's, namely raising the level of distribution at the cost of restricting things to smooth numbers, say? Can that sort of thing ever help?
Yes, it definitely can help. So for when you're looking at intervals containing a very large number of primes, I showed that you can have m primes in an interval of roughly e to the 4m. This 4 is corresponding to the 1/4 in your log k. So again, if you have a high level of distribution, you can improve that constant 1/4. For the problem of many primes, the restriction to smooth numbers is somewhat irrelevant. It doesn't matter too much at all, and so you very quickly get an improvement in that constant 4 to a constant of 3.8 or 3.9 or something like that by using Zhang's results and the refinements of the Polymath 8a project. For the question of just pairs of primes, currently the values of k numerically that we're looking at are suitably small that it appears there's a very limited, there should be a numerical benefit by incorporating ideas along Zhang's line, but these seem to be numerically suitably small, but they wouldn't necessarily give any improvement whatsoever in the number 246. but would have a large amount of theoretical computational difficulties. So maybe they could improve 246 to 244, 242, but even that's not totally clear because we're in a numerical regime where the increase in level of distribution isn't so great compared to the cost of restricting to smooth numbers or numbers that look smoothish.
I see, and that's true not just for Zhang's particular result, but for hypothetical stronger versions thereof.
So if you could prove a strong enough version where you're flexible enough in terms of smooth, what you mean by smooth, and strong enough in terms of your level of distribution, then you would expect to be getting correspondingly bigger and bigger increases. So again, it's very continuous, but at the current best known numerics for Zhang's results, we're in a regime where the benefit is almost negligible.
Excellent. Other questions? Well, if not, let us thank James again.